and it's going to go to 2 carbon dioxide molecules and 2 H2O molecules. And what the question gives you is the standard enthalpy change of formation of minus 394 and water. So the formation of water of H2O 6. Okay, let's have a look. What do we mean by that? So what we mean in terms of formation, so we'll have a look at the first one, ethane. The carbon in its standard state, which is a solid, plus its standard state would be a molecule, a gas, 2 of them. And we're going in this direction. We're forming it. And our energy that it will take is positive 52 kilojoules. To form this carbon dioxide, and from carbon to carbon dioxide, we need 2 of them. And one is minus 394, so let's change to red. I need 2 times minus 394 for the production, for the creation of carbon dioxide, for 2 water molecules. So we are going from the standard state. I'm a tad bit lazy because I know I need to add in oxygen, but I haven't done that, and I'm not going to do it yet. So we're at water, 2 lots of minus 286. Okay, so and let's get the calculator out. Calculator. Okay, so we've got minus 394, we've got 394 times 2, 788, we've got 286 times 2, 572. So we've got 572, that's 788. 572, that's 788. 1,360, and it's a minus. 1,360 minus, and that's the number of kilojoules. Okay, so we now, and I'm still on red, we're trying to work out the energy change this direction, and we're moving in this direction. For all those doing A-level maths, you'll notice that this is a line of almost a vector, but I'm going against my arrow, so I'm actually increasing. So this is not going to be plus 50, it's going to be minus 52. So I'm actually going to add on another 52 to that, which will be minus 1,400 kilojoules more. And that, the enthalpy change. I hope it sense. Alright. Striking, this is question 1A from I think 2010 paper unit 1. And if we look at this question, we're looking at the extraction of tungsten from tungsten oxide. The big clues, if you don't know, is state the role of hydrogen in this reaction, and it gives us a number of different things to look at. First of all, if I'm looking at this, I think, ooh, hydrogen, WO3, I need tungsten, and that'd be W by itself. So I'm probably going to be getting rid of the oxygen. Well, I am. So hydrogen must be acting as a reducing agent. And forgive the writings, I get used to my brand spanking new. Hydrogen's acting as a reducing agent. And then we have to write an equation. Well, it's not so complex if you think that, well, what we want to do is we've got tungsten oxide, WO3, hydrogen to it. And it'll be hydrogen gas, which is a molecule. And what we will be forming is the metal, W, and, well, the only possible thing is water, H2O. So now we have to, after looking at that, is balance it. Well, me being me, I'll look straight at the oxygen atoms. I've got 3 here. One oxygen atom, and if I've got 3 oxygen atoms here, I'm going to need 3 water molecules, because that'll give me a total of 3 oxygen molecules, which is the same here as here. If I've got 3 oxygen molecules, 3 water molecules, I'm going to need 6 hydrogen atoms, which means 3 hydrogen molecules on this side. Okay. State 1 risk of using hydrogen gas in metal extractions is the reason why I go into chemistry. It blows up. Well, there's a risk of it blowing up. And there you go. Let's rock and roll. Question 7. Consider the following reaction. Hey, what have we got there? Bromopropane plus calcium hydroxide, and we switch. Oh, so it's a substitution reaction. And we've got OH, we turn it into an alcohol. So we've got an OH, that must be OH minus. Attracted to the positive. Right, this is nucleophilic. Oh, and there's a question, this is nucleophilic substitution. Let's put the pen on. Name the mechanism. This is nucleophilic, nucleophilic sub. And the way I worked it out was nucleophile, phile is to like. Nucleo, the nucleus is positive. So something attracted to the positive will be something that's negative. The OH must have been at some point in this at OH minus. So the minus is attracted to the positive, so this is a nucleophile. It likes positive charges. It's a nucleophile substitution because we are switching a Br for an OH. So let's have a look. The mechanism. Well, let's keep the diagram like that. CH3, C, hydrogen there, CH3. And while I'm drawing, there's a thing to think about. Is a bromine species here. It's electron negative, quite highly electron negative, and it's pulling the electrons towards itself. So you've got a slight positive delta, positive charge there. Okay. Now, what we have is the hydroxide ion, OH minus. And now, oxygen, when it's attached to many things, has a lone pair. So we've got a negative charge, we've got a lone pair. Now, this lone pair is going to move. This lone pair is going to, we've got to draw an arrow moving to just outside a carbon atom. And all of a sudden now, and if you think about it very quickly, we've got 1, 2, 3, well, 1, 2, 3, 4, 5 bonds. Can't have it. And what's going to happen is the electrons, and I'm very careful, I'm drawing the arrow from the bond to the bromine. These electrons go to the bromine. And I kind of have it in my head that bromine's highly electron negative. It's going to take both the electrons, and I've got to end up with a negative charge. And what this will form is CH3, the carbon atom, hydrogen, CH3 over here, and the alcohol group there. And that's the mechanism. Personally, I'm in a habit. I read beer with Br minus as well, or with HBr. But this is Br minus is habitual. And the whole thing is three marks. One for the nucleophilic substitution, one for the arrow from the lone pair from your hydroxyl ion going to your carbon atom. And you just got to be really careful. Your curly arrows must start and finish the correct places. That's question 7A. Okay, let's get rid of the chemistry thing. Let's have a look at this one. Copper is extracted from the ore, chalcopyrite, in a three-stage process. In the first stage of the extraction, the chalcopyrite is heated with silicon dioxide and oxygen. Balance the following equation for this first stage in which copper 1 sulfide is formed. Alright, let's have a look at it. How would for diagrams. Let me move this up a bit. So while I'm looking at it, and the thing that catches my eye first is there's no number prior, so they've given us gaps. They've given us gaps to put numbers in, but here, copper sulfide, you don't have one, so I can't, shove a 2 there. And so what I'm going to do, I'm just going to kind of delete that 2 that I just put in, because I can't shove a 2 there. Let's get rid of the 2. That means that if I can't change that, I can only really have 2 copper atoms. If I've got 2 let's try again. 2 copper atoms here. I must have 2 copper atoms here. Well, you see, I can't change this. I can't. There's absolutely no way. And this is my only source of iron ions. Well, how many iron ions have I got? Well, 2. So then I must have 2 here. There's no way I can alter that. Alright. So then it goes a little bit trickier. Well, this is my only source of silicon. There's no silicon here, there's no silicon here, so this is silicon. I must have 2 atoms of silicon. If that's the case, this must be 2 there. Alright. Well, now we're having a look at it and we think, okay, let's have a nosy. Let's have a nosy at what's going on here. Sulfur dioxide. So I can't count my oxygens yet because I don't know how many oxygens on either side. I don't know how many atoms I've got there or how many atoms I've got there. That is in the sulfur. When I come across here, well, do I know how many sulfurs I've got? Well, yeah, this is the only source of sulfurs for my reactants, and I've got 2 in the species and 2 molecules of that, so I must have 4 in total, 4 sulfur dioxides. Hold on, that doesn't look right because I've forgotten. Oopsie daisy, I've forgotten, haven't I? There, I'm tinkering away. I haven't noticed what we're actually making. Copper sulfide. And I'll just delete that for a moment. So there you go, making a mistake. I've got sulfur here. This is 4, it's 3. Alright, so that's 3. Well, now I know all, I can find out all my options on this side. 3 times 2 is 6. 3 times 2, I've got 12 options on this side. Well, how much have I got here? 4 and 12. We need 8 more. 402. Yeah, that's right. Okie dokie. 8A2. Give one environment reason why the SO2 gas formed in this reaction is not allowed to escape. Acid rain. Do me. State one use for sulfur dioxide formed in this reaction. There's a whole host, but the only one I kind of really remember is the manufacture of sulfuric acid. Because sulfuric acid is quite a useful product. Which is other things as well. Plaster, the kind of, those kinds of things. But the one I can really remember is the manufacture of H2SO4. Okay, not enough room to answer 8B, so I think I'll leave that one for the next little clip. Okay. Given condition needed to favour the reaction shown in part B, so it's the elimination reaction, rather than that shown in part A. We have 3 possibilities. It all depends on what you remember. Well, let's go for a couple. You could have an alcohol solvent. This reaction could be under reflux. There's another one in my brain somewhere, I just need to find it. Alcohol solvent, reflux, high conc, very high, a very high conc of potassium hydroxide. That'll favour B over A. Right. Alkenes can be polymerized. Again, this is one of those ones that you need to remember. This is addition polymerization. Polymerization. Alright. Name the alkene that gives a polymer with a repeating unit shown below. Alright, let's have a nosy. So what we're going to have to think about is, well, if that's a repeating unit, I must have had a double bond in the centre. So I must have a H there CH3 there, CH3 there, a hydrogen here. So let's name this thing. 1, 2, 3, 4 carbon atoms. So it's a butene. I've got to be careful. You see, butene can either be a double bond on the first carbon, and there we got it. Double bond on the second carbon. This is but-2-ene. It has to have a but-2-ene in it. Well, that was nice. I quite like that one. Okay, let's continue. Question 2. And I really like these questions. The balance between enthalpy change and entropy change determines the feasibility of a reaction. The table below contains enthalpy formation and entropy data for some elements and compounds. Explain why the entropy value for the element nitrogen is much greater than the entropy value for the element carbon, graphite. Okay, so, I'll put a pen on, let's have a look. I was reading that without underlining my keywords, which is a habit I like to get my students into. So we're going to have a look at, explain why entropy value, so we're looking at here, S, entropy value is greater for nitrogen, so here we have nitrogen at 192, than the entropy value for the element carbon, graphite, at 5.7. Okay, so, and it's a 2-mark question. The 2 marks in the first thing is that nitrogen is a gas, and carbon, should be a not need to that, and carbon is a solid. So that's your first mark. And your second mark is to justify your reasoning to explain why this affects entropy. Because nitrogen is a gas, therefore we could write here, therefore nitrogen is much more disordered. I love entropy. It's kind of a crazy idea, but I like it. Therefore, nitrogen is much more disordered. Let's write disordered here. Okay. Now, suggest a condition under which the element carbon, diamond, would have an entropy value of 0. Now, the first time I saw this, I didn't actually read the diamond. And I thought, oh, carbon, how would we get this entropy to 0? And one of the things I would do is make it diamond, because diamond had all the bonds joined together and there's no sliding sheets. But it's talking about diamonds that's already done that, and the only other way to drop entropy and actually get to 0 is at absolute 0. Absolute 0, or not Kelvin, or minus 273 degrees Celsius. However, you put it at 0 Kelvin, the entropy just doesn't exist. Okay, my hard one, write the equation that shows the relationship between delta G, Gibbs free energy, is equal to enthalpy change, delta H, and from that you need to take away, you need to subtract delta S. But as you can imagine, disorder is dependent on temperature, and the higher your temperature, the greater your disorder. Because you can just imagine, if we just look at water, for example, water at 90 degrees is a lot less disordered, a lot less entropy than once you get to 110 and it's a gas. So temperature is essential to have temperature here. To be honest, I think it's such a important idea that we need to, I'm going to put it in red, T delta minus T delta S. Okay, there you have it. The equation that shows the relationship between delta G, delta H, and delta S. Okay, yeah, you can have different variations of it. You can, however you've remembered it. I'm quite bad at it because as I get older, my memory's going. But I kind of think of the ideas. It kind of helps. Okay, let's switch the pen off and let's just scroll down a bit. So looking at 2D, it's a state the requirement for a reaction to be feasible. And what we're looking for there is when we calculate delta G, it's got to be less than or equal to 0. Right? And there's me writing it very, very formally. I love writing equations and formula and don't like using words because you can see my handwriting is disgusting. So you can either do it like this, delta G is less than or equal to 0, or write it in words. But that is question 2 done. Okay, stop recording. Alright, a student had an idea to earn money by carrying out the following reaction. Graphite to diamond. Use data from the table on page 4 to calculate values for delta H and delta S for this reaction. Use these values to explain why this reaction is not feasible under standard pressure at any temperature. Okay. Now, if it's not feasible at any temperature, that will mean delta G is always bigger than 0, no matter what happens. So if I look at the formula, delta G is equal to delta H minus T delta S. Now, you'd think the bigger this quantity gets here, at some point, no matter how big delta H is, this, take away a positive number, the point will get big enough for it to become 0. But the thing is, if we suddenly had delta H being positive, and we could somehow make minus T delta S positive, you'd always have a number bigger than 0. And the way to think about it is if we take minus T and delta S, so we've got minus T times delta S, that's what this means, then as soon as I have this as a negative, as soon as this is negative, a negative number, then you've got a negative here multiplied by a negative here, you're going to get a positive. Your number's always going to be bigger than 0. So what I'm expecting is, I don't really care about delta H, but I'm expecting it to be positive. I'm expecting it, because if it's negative, well, it's going to be a spontaneous reaction at some point, but I'm expecting it to be positive. I also expect delta S to be negative. So I'm expecting this one to be positive and this one, delta S, to be negative. Alright, so let's get back. I'm just going to pause it because I'm going to bring in both questions. So let's just put this on pause so we can see all the data, the table next to it. Okay, so what I've done is I've brought it, copied and pasted the question here. Spare me a tick. Okay, so as I said previously, what I was expecting and what we're expecting, let's get back to the right page, it does help, is delta H. Now, delta H, the enthalpy of formation of diamond, and we'll do it in blue, is here. Graphite is 0, so the calculation for delta H is the sum of the products minus the sum of the reactants. The products is nice, it's 1.9, the reactants is nice, it's 0, so delta H here is a positive 1.9. So let's have a look at delta S. So again, sum of the delta S for the products minus sum of the delta S of the reactants. So the product is 2.4. I need to take away from that, I need to subtract the reactant, which is graphite, which is 5.7. So getting my crazy calculator out, and I do suggest you always use a calculator for this, because as much as many you can do this in your head, it is really easy to make a arithmetic error, and to be honest, really not worth losing the marks. So as I pop this in, and it also ensures you get the right signs, minus 3.3. So delta S, I'm expecting here, oops, it's all cleared. So we have minus 3.3. And for enthalpy formation, we have positive 1.9. So as I said, because the formula is delta G equals delta H minus T delta S, because we have minus T times a negative, there's always going to be a negative, in this case minus 3.3, we will get for this part of the expression a positive answer. Delta H is positive 1.9. So delta G, no matter how big your temperature gets, it's always going to be a positive answer. So the explanation is delta G will always be positive. That says positive, believe it or not. Okay, that's that one done. And roll. We're going to be looking at group 7. Periodicity, this tends to be OCR unit 1. Just felt like it. Let's have a nosy. Okay, so what we got here, we got his little blue pen. Right. A student used the internet to research chlorine and some of its compounds. He discovered that seawater contains chloride ions. The student added aqueous silver nitrate to a sample of seawater. What would the student see? Okay, this is an interesting way of asking a question about the test for group 7s. The test for group 7s are silver ions. I'm just going to pop that there. Ag plus, that's silver ions. The reason why it's a test, for all intents and purposes, all nitrates are soluble. So silver nitrate is soluble. But silver ions, when they're added to chloride ions, so here we've got it in seawater, it forms silver chloride, AgCl. AgCl is insoluble. So what will the student see? The student would see, you could turn around and say a white solid, or, this is horrible writing, I've just got to get used to it, a white solid, or a white, and it's got to be white, or a white precipitate, PPT, precipitate. Okay, so the next bit, write an ionic equation including state symbols for the reaction that occurred. This, although it sounds, you've got to kind of get used to it, an ionic equation, what it's asking for is how do you make the precipitate? How do you make the silver chloride? So we've got 2 marks. The first one's for the reaction. So what we're doing is we're making silver chloride, AgCl. Now, I kind of threw that one in over here because it sticks in my head. But we'll look at where I got AgCl from as well. We said it was a precipitate. We said it was a white solid. So we'll put little states of being solid over here. And how do we make this? I'm not interested in the chloride ions or whatever other ions are in there. I'm only interested in the formation of silver chloride. So, silver is Ag+, something you have to memorise. And what we're going to add to it are chloride ions. Group 7 Cl-. And that will get you 1 mark. We're not interested, I just said it before, we're not interested in the nitrate over here, the silver nitrate. We're only interested in the ions that make up silver chloride here. Ag+, the silver ion here, was in the form of silver nitrate before we added it to the chloride ions. This is in solution in seawater, this is Aq. The chloride ions in seawater over here, this is Aq. These 2 aqueous solutions. Okay. After carrying out the test in 1, the student added dilute aqueous ammonia to the mixture. What would the student see? Okay, so what happens is, the thing to remember is when you have silver chloride, it's got to be aqueous ammonia. If you add dilute aqueous ammonia, the precipitate, you could turn around and say dissolves, so PPT, the precipitate dissolves. Yeah, you can also describe it in other ways. You can turn around and say it disappears, if I can spell disappears. I think I might need 2 P's in there, but I'll get the idea of the fact that it goes clear. Right? Okay. The student also dissolved that chlorine, the student also discovered that chlorine is used in large-scale treatment of water. State one benefit of adding chlorine to water. Okay, I would say, sorry, one back, that chlorine is really toxic and it kills, these are bacteria. Right? If you're not doing A-level biology, you could even say it kills germs. But your terminology, your aim is to describe the fact that it's killing the nasties, kills bacteria, microorganisms. And if you're again not a biologist, you could even turn around and say it makes the water safe to drink. So I've taken my time on that one because there are some students who don't do other sciences. All right. Not everyone agrees that chlorine should be added to drinking water. Suggest one possible hazard of adding chlorine to drinking water. Okay. Again, the number of things you could write. It's not nice. It's toxic. All right, it's not nice. It's toxic. It's like poisonous. Poisonous. That will do. Okay, let's get rid of this pen. Control. No, I've changed to pink. That's really good. Actually, I think what I might do is just switch this part off and do another video. No, there I go. I'm fine. I'm going to scroll down. I'm going to scroll down to